about explosions. No, none of those. I'm thinking of the biggest explosions in the modern universe, star explosions or supernovae. Supernovae release an unfathomable amount of energy. A supernova can outshine an entire galaxy. And if one was to happen in our galaxy, it would be visible even during the day. But all of that light is only a fraction of a percent of the energy from the explosion. Almost 99% of the energy from a supernova is carried off by my favourite particles, neutrinos. Today on Even Bananas, we're going to talk about what these tiny, hard-to-spot particles can teach us about the biggest explosions in the universe. You might have heard the phrase, "we are all star stuff," and it's true. Stars make almost all the elements that are vital for life, and supernovae are a really important part of that process. When a star explodes in a supernova, that's when it makes the heavy elements, and the explosion flings matter in all directions, allowing the future creation of planets and, on at least one planet, bananas. If stars are the kitchens where the ingredients for life get cooked up, supernovae are the delivery trucks bringing those ingredients to your neighbourhood. But supernovae also produce neutrinos. We're talking a lot of neutrinos, like a disturbing amount. A supernova will release more neutrinos in the span of a few seconds than over the rest of the star's entire life. And it's not exactly like stars are slacking on the neutrino production front before they explode. Hold out your hand. Don't be shy. In the time it takes me to say this sentence, several trillion neutrinos from the sun will pass through your hand. Almost none of those neutrinos will interact with your hand though, because neutrinos barely notice we exist. But if we can spot these explosions, neutrinos could teach us a lot about the end of a star's life. Stars that go kaboom could end up as a neutron star or a black hole, but we don't fully understand how that whole process works. One way to figure some of that out is by watching a supernova happen from beginning to end, and we can do that with the help of something called snooze. Not that snooze. I'm talking about the supernova early warning system. And I know it kind of sounds like some sort of natural disaster alert. But fortunately for us, the stars in the Milky Way that could go supernova soon are a nice, safe distance away, so they don't pose any danger to us on Earth. To tell us more about snooze, what it is and how it works, let's talk with Fermilab scientist Anna Schukraft. Anna studies neutrinos from space and from neutrino beams we make at Fermilab, and she works with me on the Microboon and June experiments.
Hi everyone! Snooze began in the early 2000s. It's a group of 7 neutrino detectors around the world feeding into a central system. If they see a spike in neutrinos simultaneously, Snooze can say, "Look, a supernova." Snooze is exciting for astronomers because when a star does go supernova, the neutrinos arrive at Earth several hours before the light arrives, giving them a big heads up.
Now, I know that sounds like neutrinos are going faster than light, but stay with me because they're not. Remember, neutrinos only interact through gravity and the weak force, which is weak. Photons, or particles of light, on the other hand, interact through gravity, the weak force, and the electromagnetic force. So neutrinos leave the core of a supernova barely disturbed, while photons get jostled and bumped around on the way. Anna has a really great way to describe what's happening.
I like to think of it this way. Usain Bolt and I both go shopping and when finished, try to exit the shop at the same time. We can all agree Usain Bolt is faster than me. But as people stop him to ask for an autograph, I'll sail right through the exit. That's what happens in a supernova. Neutrinos travel just slightly slower than the speed of light, but they still arrive before the light does because the light got interrupted.
So back to snooze. Remember, it's a network of 7 neutrino detectors across the world. If any experiment detects a potential burst of supernova neutrinos, it sends data to a central computer. If 2 or more detectors spot a burst within 10 seconds of each other, the computer automatically alerts its mailing list. And of course, there are lots of checks built into the system to avoid false alerts. In fact, Snooze has never actually sent out a supernova alert, so it's not the most busy computer. 2 experiments at Fermilab are signed up to get the alerts if one is sent, Microboon and Nova. And Nova is actually working towards becoming one of the experiments feeding into the network too. So the next question you're asking might be, have we ever spotted the neutrinos from a supernova before? Let's hear more from Anna.
We have successfully spotted supernova neutrinos once, from supernova 1987A in 1987. We saw a total of about 24 neutrinos across 3 neutrino detectors worldwide. Astronomers see hundreds of supernovae each year, but only ones in our galaxy are close enough for us to spot the neutrinos from them. We expect 2 or 3 supernovae in our galaxy per century, and there hasn't been one since 1987. If one happened tomorrow, we would expect to spot tens of neutrinos in nova. That doesn't sound like much, but our accelerator normally fires trillions of neutrinos at it each day, and we only see a couple of neutrino interactions. Dune, an experiment we're building over the next 10 years, would see thousands of neutrinos from a nearby supernova. That would generate up to 100 terabytes of data in a minute, which obviously presents a big computing challenge.
So, what would we learn? If we could see all the neutrinos from a supernova over the whole explosion, that would really help us understand how core collapse supernovae happen, because we could watch it happen in neutrinos. Of course, it would also be a great source of neutrinos in our detector, and we could study those to learn more about the properties of neutrinos themselves. All in all, it's pretty exciting stuff. As we keep building better neutrino detectors, we'll have even more opportunities to spot neutrinos that have travelled from space to share their secrets with us. And if we're lucky enough to witness a supernova in our galaxy, Snooze will be ready to share the news. That's it for this episode of Even Bananas. If you're enjoying the series, share it with your friends and subscribe so that you can get an early warning when we're back with our next episode.